So the next topic is flanged bolt coupling connection. And this is second to the last topic for this course. So we still have shear and moment in beams after this. So let's talk about coupling connection. So in a shaft, or in a shaft connection called flange bolt couplings, the torque is transmitted by the shearing force P created in the bolts that is assumed to be uniformly distributed. For any number of bolts n, the torque capacity of the coupling is P equals PRN, or equals pi d squared over 4 tau Rn. So P here, okay, is the force creating your torque. Okay, so that's your P. So for example, in this coupling connection or in this coupling connection, okay, this is the shear force creating your torque, since this force is at a distance from the center of your figure. So remember, whenever you have an offset force not directed at the center, it creates moment, or in this case, torque. And then R is the radius, distance of your force to the center. So it still follows the equation T equals RF. Again, R radius, F is force. So here it's PR. Okay. And then N for the number of bolts. Okay. And then recall, shear force is also equal to shear stress times area. Shear stress is denoted by tau area. This is the area, cross-sectional area per bolt, since they are the ones experiencing shear stress. Cross-sectional area of a bolt is a circle. That's why the area is pi d squared over 4. And then once again, N for the number of bolts. Okay. Next, if a coupling has two concentric rows of bolts, the torque capacity is P, again for torque or torque capacity, it's P1 R1 N1 plus P2 R2 N2. So if it's 3 rows plus P3 R3 N3. So P, R, N are the same. P, force, shear force being experienced by that bolt along that concentric row. R is radius to the center, and its number of bolts in that row. For example, here is your first row, or rather the outermost section. This is your first row. So there's 1, 2, 3, 4, 5, 6 bolts there. So N there would be 6. P1 is P1, R is whatever that distance of each bolt is to the center. And then same for R2. Okay, this is your second concentric row. So we have 1, 2, 3, 4. That's your N. Then P2, R2. Now the relationship between P1 and P2 are the following. P1 over A1 G1 R1 equals P2 over A2 G2 R2. So for example, you're only given the shear force in one concentric row. To get the shear force, or P, in the other row, you'll use this equation. Again, P is your shear force or parallel force to your bolt. A is cross-sectional area, G is shear modulus, and then R1 is radius. Okay, and this is a 3D view of what coupling connections look like. Right. Next, so for rigid flanges, the shear deformation in the bolts are proportional to their radial distances from the shaft axis. Basically, from that, you can derive the equation shear stress 1 over G1 R1 equals shear stress 2 over G2 R2. So shear stress, again, is just your shear stress in each bolt for each concentric row. G is modulus of rigidity or shear modulus, and then R is distance of your bolt to the center. Okay? Do you have any questions so far for the concepts of coupling connections? Please answer in the chat again. Okay. So I'm not going to derive these equations anymore. You can just try to memorize them. Okay. Since you don't have questions, let's have some examples. Number 1, a flange bolt coupling consists of 10 20mm diameter bolts spaced evenly around a bolt circle, 400 millimeters in diameter. Determine the torque capacity of a coupling if the allowable shearing stress in the bolts is 40 MPa. The first step is the same, write your given. So flange bolt coupling consists of 20 millimeter diameter bolts. So that 10 is your number of bolts, so that's your N. N equals 10. What else? 20 millimeter diameter. In our equations, we're using radius. So we have 10 D equals 20 millimeter. And then radius is 10 millimeters. Okay? That's just over 2. And then allowable shear stress, 40 MPa. What are we looking for again? We're looking for torque capacity. So we're looking for T. Let's look at our equations for T. We have two, either PRN or pi d squared over 4 shear stress Rn. Now we're going to use what's available or what variables are available. Okay, now look here. In our problem, what's given is shear stress and dimension. We're not given the shear force. So therefore, we're going to use the equation pi over 4 d squared shear stress. Okay, so let me write that out. So torque capacity is pi d squared over 4 tau Rn. Okay, then it's just a matter of direct substitution. Pi diameter is 20, so 20 squared over 4. Shear stress is 40 MPa. PA ba? Yep, 40 MPa. Radius, 10. And the number of bolts. 10. Wait. Is it 400? 200. 400 millimeter diameter. Okay. So 200 millimeter, not 20. So R is 100 millimeter. Shear stress, 40 MPa. So these are the dimensions of your actual bolts. Next, 400 millimeters in diameter. That's the dimension of your row. So that's capital D to distinguish it from the diameter of your bolts. Therefore, capital R is 200 millimeters. Right. So pi, no, it's 20. Okay. So lang yung 400. Okay. So pi d squared over 4 times 40 times R. Capital R is the radius of your row, concentric row, or in short, distance of bolt to center. That's capital R. So that's 200. And the number of bolts is 10. Please compute. What's the answer? Again, please compute. Correct. Sierra and Nina Flores Gutierrez. So this is a new topic, so new recitation. Gutierrez Flores. Okay, good. So it's a bit long. 2000 3 2 7 4 1.23. This is Newton millimeter. To make things shorter, you can convert it to kilonewton meter. So that's divided by 10 raised to 6. So this also equal to, so divide by 10 raised to 6, 1, 2, 3, 4, 5, 6. That's 25.13 kilonewton meter. Okay, so that's how you convert Newton millimeter to kilonewton meter. Divide by 10 raised to 6. Okay. So your final answer will depend on what unit the problem states. Since there's no unit mentioned, just write. Okay, so that's number 1. Any questions for number 1? Please answer in the chat. Okay, no questions. Let's move on to number 2. Okay. Number 2. Okay, let's read. Flange bolt coupling consists of 8 10mm diameter steel bolts on a bolt circle, 400 millimeters in diameter, and 6 10mm diameter steel bolts on a concentric bolt circle, 300 millimeters in diameter, as shown in the figure. Letter A, what torque can be applied without exceeding a shearing stress of 60 MPa in the bolt? Letter B, determine the number of 10mm diameter steel bolts that must be added on the 400mm bolt circle of the coupling to increase the torque capacity to 14 kilonewton meter. Okay, so there's a lot. So basically, we have 2 concentric rows with the following properties. We're looking for letter A, maximum torque that can be applied without exceeding or shearing stress 60 MPa. So it's similar to what we did for number 1. And then letter B, determine the number of 10mm diameter bolts that must be used on the 400mm bolt circle of the coupling. So that's just how many additional bolts can I add to the concentric row so that the torque capacity increases to 14 kilonewton meter. Okay? So let's start with the first step, right? The given. So 8 10mm diameter steel bolts. Let's call that N1. Okay. N1 is your 8. Then D1 is your 10mm. Therefore, R1 is 5mm. Actually, I don't think I need that. And then bolt circle 400 millimeters in diameter. So that's the property of the concentric row. So that's capital R. Or in this case, it's diameter, so capital D. 400 millimeter. To get capital R, that's just divided by 2. There. Next, N2. 6, 10, 300. 6, 10, then 300. And then once again, you want R1 to get R2, divide by 2, 150 millimeter. Okay, what else? Shearing stress 60 MPa. And then, that's it. So let's start with letter A. So we have 2 concentric rows, right? And then each of them can't exceed a shear stress of 60. Now let me ask you, which row is more critical? Critical meaning that is where we'll base our design on or our computations on, meaning it's the one experiencing the most stress, okay? Is it row 1, the outer row, or the inner row? So 1 or 2? Row 1 is the outer row, row 2 is the inner row. Which row experiences more stress, row 1 or 2? Okay, everybody answer. Okay, very good. Correct. Jade, Audrey, Tim. Lumibaw, Manrique. Anyone else? Okay, so the answer is 1. Why? Again, shear stress is shear force over A. In this case, it's P. It's denoted as P. And P is torque. And what's the equation for torque? That's RF. R being distance from your axis or center. So the farther it is from the axis, the greater its force, therefore the greater its shear stress. That's why row 1 is the more critical row. So that is where we'll base our equations on. So that is where we'll base what P is. Okay, let's solve. So P1 is, again, we're going to use one of the two equations. We can use this. Okay, so P1, which is equal to P. P1, which is equal to shear times area. Since this is shear force, so shear force is shear stress times area. Okay, shear stress is limited to 60. So 60, and then area, again, this is a bolt. Cross-sectional area is a circle. So pi over 4, diameter of bolt, 10 millimeter squared. What's the answer in pi? Correct, Trinity? Who else? Correct, Philip. Okay, it's 1,500 pi. Okay, so the reason why I wanted it pi so that I don't have to store this in my calculator. Right? Okay, next. Now that I have P1, how do I get P2? Okay, now you might think to get P2, we're gonna do 60 times pi over 4, and then D2 is also 10 squared, you'll get 1,500 pi. No, that's not how you do it, okay? Because whatever the force of P2 will be dependent on the force of P1. Okay, they're not acting independently from each other. If there's a single torque applied here into your system, P1 and P2 are dependent on each other. So you can't do that. So this is very wrong. Instead, remember, we have an equation for this. And I'll show you. Yeah. P1 over AGR equals P2 over AGR. Okay, so that's what we'll use. So P1 is 1,500 pi. Over area 1. They have the same diameter, right? Bolt diameter. They're both 10 millimeters. They have the same area, therefore we can cancel that. They're of the same material, therefore they have the same modulus of rigidity, which is not given. Is it given? It is not. But since they're the same material, there's no mention of different materials here. Modulus of rigidity is also the same, so you can cancel that. So you're left with R1 and R2. R1 is 200 millimeters, and then equate this to P2 over R2, which is 150. Please solve what's P2. In pi. Okay. Correct, Trinity, and kulang sagot mo, Jade and Audrey. Wala ba? Okay. It's 11255. Again, I just want pi so that I'm not storing your calculator. You can just use the decimal place if you want as well. Just make sure to store it. Okay, now we have P1 and P2. Let's refresh ourselves. What are we looking for? Maximum torque that we can apply. So we have two concentric rows. Maximum torque would be the summation. Yeah. Maximum torque is the same as torque capacity, so it's just summation of PRN. Okay, so let's do that. So torque capacity or torque P1. So my tablet is acting up. So P1, R1, N1 plus P2, R2, and 2. P1 is 1505, R1 is 200, N1 is 8, plus P2 11255, R2 is 150, and 2 is 6. Please solve as the final answer. Correct, Miguela and Laika, Muni and Okay, so it's very long again. I'll write it here. 107,206,84.93. And again, this is Newton. Millimeter, or divide 10 raised to 6. So just move 6 decimal places. So 10.72 kilonewton meter. That's the answer for letter A. Next, let's move on to letter B. And what's letter B? Additional 10 millimeter diameter bolts on the 400 millimeter bolt circle to increase torque capacity to 14 kilonewton meter. So now our torque capacity is 14 instead of 10. We're adding on the 400 coupling, so meaning that is at N1, okay, because that's your 400. Therefore, this would be your equation. Okay, so we're still following P equals this P1. Okay, so existing P1, P1, R1, and 1. So we have N. We're looking for additional. Okay, we're not looking for additional. We're just looking for the number of 10 millimeter bolt that must be used. Okay, so we're looking for just N, not the additional N. So N1 plus P2, R2, and so now this is 14. So you can convert it to Newton millimeter, multiply by 10 raised to 6, and then solve. P1 is still 1505. R1 is still 200. And this is what we're looking for N, or N1, since it's on the 400 millimeter row. And then plus 11255, R is 150, N is the same, it's 6. Please solve what's N. Correct, Beatrice? Rebea? Who else? Correct. Philip. Okay. The answer is 11.48. You can have a portion of a bolt. So whenever number of bolts is asked or number of something is asked, remember this sign always needs to be more conservative, meaning it gives more space for rounding off, more space for loads. Okay, we're always rounding up. So say round up, we need 12 volts. Okay, and that is number 2. Any questions for number 2? Please answer in the chat. Okay, no questions. Let's move on to the next number, 3. No figure again. A flanged bolt coupling consists of 6 half-inch steel bolts evenly spaced around a bolt circle, 12 inches in diameter, and 4 3/4-inch aluminum bolts on a concentric bolt circle, 8 inches in diameter. What torque can be applied without exceeding 9,000 psi in the steel or 6,000 psi in the aluminum? Assume modulus of rigidity of steel is 12 times 10 raised to 6 psi, and for aluminum, 4 times 10 raised to 6. So once again, we're given 2 limitations or restrictions. One for shear stress in steel, the other is shear stress in aluminum. Okay, so again, we're just going to compute for T for both and then compare which should be our final answer. First step is the same, write the given. 6 half-inch steel bolts. Okay, so let's write that out. Let's say NST for steel, 6, half an inch for the steel bolt, so half an inch. And then bolt circle, 12 inches, so that's your capital D. And then we need the capital R, so that's just divided by 2, 6 inches. Next, 4 3/4-inch aluminum. So NaL for aluminum. Diameter of aluminum bolts is 3/4-inch. Okay. Diameter of concentric circle is 8 inches. So 8. And then radius is divided by 2. 4 inches. What else? So maximum shear stress in steel is 9,000 psi. So shear stress in steel, 9,000 psi. And then shear stress in aluminum should not exceed 6,000 psi. Okay. Then GST and GAL. So GST is 12 times 10 raised to 6 psi. GAL is 4 times 10 raised to 6. Okay. And that's it. Let me just fix this more. Okay. 6 psi, psi. Okay, so that's all the given. So what are we gonna do? Okay, again, the restriction is for the shear stress. Then we have 2 concentric circles. The first step is to figure out, we're looking for the torque that it can withstand or can be applied without exceeding everything. As mentioned earlier, just to get torque capacity, you're just gonna get the summation of PRN. Let's try doing that. P1, R1, and 1. However, as you can see, there's no P. So instead of P, it's shear stress times area, or pi over 4, or pi d squared over 4 times shear stress times R. So 1, 1, 1, R1, and 1. Okay, let's make this larger. Okay. Pi d1 squared over 4 times shear stress of steel. So this is steel, shear stress of steel, R steel, and steel. Then plus pi d of aluminum squared over 4, shear stress of aluminum, R of aluminum, and of aluminum. Okay. Next, plug in our given values. So pi dst is half an inch. So let's just call that 0.5 squared over 4. Now what about shear stress? Well, I just plug in 9,000 and 6,000 and get the value for torque capacity. The answer is no. Because again, the force being experienced by one row is dependent on the other row. Okay? Meaning, you can't just solve each separately. Meaning, I can just input 9,000 and 6,000 here. Okay? So what I need, okay, so this will remain as a variable, PST. Okay. RST is 6. And then NST is also 6. And then let's just continue on with our equation. Pi, diameter of aluminum is 3/4. So that's 0.75. Diba? Right. And then over 4, shear stress of aluminum. R of aluminum is 4. Number of, or N of aluminum is also 4. Now we're left with this equation with 3 unknowns. Okay? And again, shear stress is independent on each row. So we cannot just plug it in. So what do? We need another equation relating shear stress to each other. And luckily, we have that. You remember we have this. Shear stress 1 over G1 R1 equals shear stress 2 over G2 R2. Okay? So now let's just call this equation 1 for the meantime. Equation 2 will come from this. So instead of 1, it's steel, shear stress of steel over G1 R1. So G steel R steel equals shear stress of aluminum over G aluminum R aluminum. Then plug in your values again. Shear stress is unknown. We can't get that yet. So it will become shear stress multiplied by this. So GAL is 4 times 10 raised to 6. Right? And then RAL is 4 equals shear stress in the aluminum times GST RST. GST is 12 times RST, which is 6. There. And then let's simplify further, right? 4 times 4, that's 16. So this is 16 times 10 raised to 6 shear stress. Plus 12 times 6, 72, right? Times 72 times 10 raised to 6 shear stress aluminum. Simplify further, we can just cancel out 10 raised to 6. Divide everything by 4. Common denominator. 8. Divide everything by 8. 16 divided by 8, that's 2. Shear stress in steel equals 72 divided by 8, that's 9. Shear stress in the aluminum. And this is your equation 2. Okay? And now, after that, since we have the relationship of ST and AL, we're gonna check for each limitation. First for the 9,000 pound, for the 9,000 psi, and then next for the 6,000 psi. Because unlike the previous example, we know the critical row. We know the critical row is the farthest from the center if it has the same material and properties. Okay. In this case, we don't know because they're different materials and they're different distances from the center. Okay. So that's why we're going through this step first. Do we have time? Let's try it. So first, using the limit for steel, shear stress in steel equals 9,000 psi. Okay. So we're gonna use equation 1. So P equals I can simplify this further pala. So that hindi marami sinusulat na. Let me simplify. Okay, let's simplify. Pi over 4 times 0.5 squared times 6 times 6, that's 9 pi over 4. Shear stress steel, and then plus pi times 0.75 squared times 4, that's also 9 pi over 4. Shear stress aluminum. Okay. And then you can just rewrite this as 9 pi over 4 shear stress steel plus shear stress aluminum. And this is your equation. Okay? Then what you're gonna do, 9 pi over 4. Plug in now your shear stress for steel. PST plus PAL. So plug that in now. 9 pi over 4, this is 9,000. And how do we get shear stress for aluminum? We're gonna use this. Shear stress for aluminum is twice shear stress of steel over 9. So plus 2 over 9 or twice 9,000 over 9. Oh, wait. 9 over 2. Yeah. Okay. And then from this, you can solve P. So can you solve, please? What's capital P? What's your torque capacity? Correct, Beatrice and Muni. Okay. 77754.42. Then unit is, these are all in PSI, so pound inch. And then if you want to keep inch to make things shorter, divide by 1,077.54 kip inch. And again, kip is just 1,000 pounds. And then compare that to this 9 pi over 4. Compare that to using the shear stress for aluminum, which is 6,000 psi. Okay, let's try to finish this. Okay, now we need an equation for steel. So shear stress of steel is 9 shear stress of aluminum over 2. So shear stress of aluminum is 6,000 over 2. plus 6,000. Please solve. What's the answer here? Correct, Jade. The answer is 233,263.25. Again, that's pound inch. Divide by 1,000 to get kip inch. So that's 233.26 kip inch. Now you have to choose which of the two is our answer, 77 or 233. Everyone, please answer. Should we use 77 or 233? They're very good, Bea and Jade and Audrey. Pascual. Okay, the answer is 77.54 kip inch. Why? Because again, for force, you're choosing the smallest value. So that's 77. Because anything that exceeds 77 will cause failure in your steel bolts. Okay? So that's it for number 3. Any questions for number 3? Please answer in the chat. Okay, great. So as a reminder, don't do the mistakes that I've shown you. Okay, again, force and stress is dependent on each other for each row. So you can't just plug in the given. All right. So I'll end the lecture there. Next meeting is continuation of lecture. On Saturday, we have modular exam 3. Quiz 3 only. And then coverage is torsion and coupling. You've already uploaded your IP exam 2, so answer that for those who got a grade. I've already completed your grade as well. So check if you need to answer IP exam 2. Okay. No more questions. So since you don't have any more questions, see you next meeting. You may go. Goodbye, class.